Hi, we're Team 6 from Section 3, and we'd love to walk you through what we've been doing over the last couple of weeks with the xLab.
So in xLab A, our team printed out the components of the assembly. In this xLab, we learned how to use Cura, a 3D printer slicing software, which we hadn't been exposed to before. And we used the Ender printers, which were also new to us, as we had mostly been using Multimakers in the past. In xLab 2B, each team member took on a separate electrical component. So we all learned how to work with those electrical components, solder, and also upload code with an Arduino to implement these electrical components so the data would read. In this xLab, we learned more about electrical components, soldering, circuitry, as well as coding in C++ and using AI to assist with coding.
xLab 2C was centered around finite element analysis to measure the theoretical ways that our shafts would break either in torsion or 4-point bending. And then we learned a lot of ways to decide on what materials to use in SolidWorks to measure materials we haven't really used before, and just got more familiar with FEA in SolidWorks. And then 2D was a complete shakedown of our device, so we integrated all the individual electrical components, and we learned a lot of troubleshooting strategies as well as electrical integration strategies.
xLab 2E was all about experimentation. So our goal here was to break as many shafts of as many different types as possible in fatigue testing. And by doing this, we gained some preliminary insights about how different shafts of varying infill geometries, number of walls, infill types, would fail in fatigue. And in xLab 2F, we put it all together and we created some summary videos in the hopes that the future generation of ME321 students would have a little bit of easier time kind of seeing the overall goal of the project, and as well as getting some kind of head start on those technical troubleshooting issues that we encountered over the semester.
Now we'll go in more depth into the ESP32, which each of us will talk a little bit about.
Originally, our team used an Arduino Uno and an Arduino Nano for the LCD and load cell, and then for the SD card and optocouplers. And upon integrating these designs, we were trying to integrate them onto the Nano itself, but it didn't have enough input pins for us to do all the components that we needed. So our group decided to kind of upgrade to the ESP32.
So the ESP32 had enough pins on its own to take in the optocouplers as well as the load cell, and it could produce data on the SD card reader and the LCD screen.
One of the main benefits of using an ESP32 microcontroller as opposed to something like an Arduino Nano is that the ESP32 microcontroller has the capacity to connect to the internet, allowing you to observe your data in terms of cycles and RPM while not being physically present in the room with your Moore assembly. One of the biggest battles that we faced when trying to integrate the ESP32 into our Moore assembly was transferring components that were already working on the Arduino Nano over to the ESP32. This is because the ESP32 requires several wiring changes as well as code tweaks to make the other components like optocouplers and SD card reader integrate with the ESP32. There were a number of ways in which this was overcome. One YouTube channel that we found particularly helpful was the DroneBot Workshop. He has a number of videos on all of the components used in the Moore assembly, but he has a particularly good video on the ESP32 in terms of troubleshooting and getting it to work with connecting to Wi-Fi. Diving into a little bit more about the code behind the ESP32 connecting to the web, we ultimately implemented two main functions, the handle root function and the handle data request function. Let's break each one down. The handle root function serves as an HTML page to clients where they access the root URL of the web server. The HTML page contains headings, paragraphs, and spans that display the RPM and cycle counter values. It also includes a JavaScript section inside with script tags. The JavaScript section defines a function called fetchData that sends an XML HTTP request to the server to fetch data from the data endpoint. The fetchData function then updates the RPM and cycle counter values displayed on the HTML page with the received data. It also sets up a timer using the set interval to call the fetchData function every 1,000 milliseconds or 1 second, ensuring that continuous updates occur without refreshing the entire page. And finally, it sends the HTML response with the status code of 200, which means OK, to the client. The second function is called handle data requests, which ultimately provides the JSON data requested by the JavaScript code on the HTML page. It does this by constructing a JSON string containing RPM and cycle counter values obtained from the variables seen in the code. The JSON string is formatted such that each value is displayed next to its appropriate counter. It then sends the JSON response with the status code of 200, which means OK, and content type with application in JSON to the client.
Despite our troubleshooting errors early on, we definitely would recommend everyone use the ESP32 microcontroller for a lot of different reasons. Two main ones are, one, it has a lot of pins, so you can plug everything in very easily without having to run into too much trouble. And two, the second main reason is that you can monitor your system remotely, which means you do not have to spend your whole weekend in Hudson, and you can run things remotely and come visit right when it fails and your RPMs drop down. So it's very, very helpful to have ESP32 and the Wi-Fi capabilities.